All right. Good morning. It's Friday, 3 December, and this is the Bayesian machine learning class. In particular, the lecture about continuous data and the Gaussian distribution. Um, just a few remarks about this class. You have, of course, worked with Gaussian distributions in many classes before this class. So in principle, there shouldn't be anything new. I think the interesting thing that I wanted to convey in this class is in the first few cells or slides, I talk about or write about why is the Gaussian distribution used so often and why is it so successful? And in many accounts, I just read, well, it has good computational properties. And that's not the only reason, right? There's a few other reasons. The Gaussian distribution has very good properties. But one reason is also that among all distributions that have the same variance, so the same spread, the Gaussian distribution has the highest entropy, which means you make the least amount of assumptions. So, and that's nice because in Bayesian machine learning, well, we have to come up with our priors, right? Let's say a prior over a parameter. And if this is a parameter that can have values over the real axis and you want to make very few assumptions, then you should probably take a Gaussian, just from the viewpoint that the Gaussian makes the least amount of assumptions among other distributions with the same kind of spread. So that's a really good reason to actually prefer the Gaussian, even if it didn't have the nice computational properties. But it does have a number of nice computational properties, right? In particular, when you do operations on probability distributions, they often tend to turn into Gaussians, right? So for instance, which ones did I list here? Any smooth function of a single rounded maximum function, any smooth function with a single rounded maximum, if you raise it to higher and higher powers, then it turns into a Gaussian function. And so if you have a particular likelihood for an observation and you have sequential observations, you basically, have the same likelihood for the next observation and the same likelihood for the next observation. So if you would do Bayesian inference, you would have prior times likelihood for first sample times likelihood for second sample, likelihood times third sample, and so forth. So you keep whatever that likelihood function is, it almost always, if you combine them all, turns into a Gaussian distribution. And on top of that, once you have a Gaussian distribution, it remains very stable because you can do a lot to Gaussian distributions and they remain Gaussian distributions, right? The product of two Gaussian functions is another Gaussian function. That means if I do Bayesian inference, a prior times the likelihood, and they are both Gaussian distributions, well, then the posterior is going to be a Gaussian distribution. The convolution of two Gaussian functions is another Gaussian function. And that means that if I add two variables, then, and they both are distributed in a Gaussian way, well, then the sum will also be a Gaussian distribution. So operations on probability distributions tend to turn to Gaussians, and once they are Gaussians, they almost always remain Gaussians. So that's really those are some good reasons why Gaussians are very successful. And then the rest of the class is just working with Gaussians, and there you just have to it's not conceptually difficult, but it's good to see a few examples. So I put in the class a few examples of how to do Bayesian inference. If you make one observation, if you make multiple observations, if you make sequential observations. And in the end, it's always kind of the same kind of thing. You have to do Bayes rule, and that means you have to multiply two Gaussians. And so the multiplication formula for two Gaussians is very useful. It's not a formula you need to know out of your head, right? But it's if you do it often enough, you will sort of naturally learn that formula. So that's what I wanted to say about this class before I turn to your questions. So now I want to open it up to you and ask you if you have any questions. Okay, Gautam.
Yes, hi. I had one question regarding one of the properties you were talking about, Gaussian distributed variable. So while in the example we were calculating the Bayesian inference for Gaussian, and we were taking, the posterior is equal to the likelihood times the prior. There, in order to apply the property of, the product of two Gaussians,
Yeah.
We do like the shift where we say like n of x given theta sigma square and n of theta given x sigma square is the same. And the reason that you stated was that the Gaussian is actually symmetric about x and the parameter theta.
Right.
Yeah, so that I didn't clearly understand. What do you mean when you say it's symmetric about x and the parameter? Like, is it? I didn't clearly understand that. Could you just
Okay.
touch on
Yeah.
that?
Yeah. Let me just share my screen. Then it will be easier to point out.
Yeah, yeah.
Okay. Just a second. Okay. So this is the well, the basic thing is that if you look at the formula here, this is for the Gaussian, right? Now, if I would exchange x and mu, then it's really the same formula. Do you see that? And so the Gaussian over x with mean mu and variance sigma is really the same expression as the Gaussian over mu with mean x and variance sigma. Because it
Oh, okay.
right. If rather than in x here, this would say mu, and rather than mu, this would say x. Well, it's still, I mean, then I get a minus. I could put a minus sign in front of it, right? And here with the same thing. So these two minus signs cancel. I have exactly the same formula.
Okay.
Yeah, and that is a very important point, because that is the sort of the only difficulty in when you do Bayesian inference.
Mm,
Because when you do Bayesian inference, I'm just scrolling down to where I can where I work that out.
yeah.
But
Yeah.
I know, yeah, I work it out here. Well, I want to show. Okay, so yeah, it's not entirely clear from here, but if I now, let's say here's my prior and here's my posterior. Sorry, this is px theta is my likelihood.
Like,
So if I want to get the posterior, I need to multiply the two and normalize. Right. So if I multiply these two, well, I get a function over. I can say, oh, I have two Gaussians that are multiplied, so the result will be a Gaussian. Well, hold on. I mean, in the multiplication formula for the Gaussian, I have to go all the way up now. Let's see. In the multiplication formula here, if I multiply two Gaussians here, indeed I get another Gaussian and a normalization factor. But this is a Gaussian in x and this is a Gaussian in x. So if this would be a Gaussian in X and this is a Gaussian in theta, well, then I can't apply this formula. So I have to have a Gaussian over the same, let's say, argument X, and then whatever these mean and variance are, whatever these mean and variances, they turn into a new distribution over X with new mean and variance, and they're given here. And this thing in front is just the normalization constant, because there's nothing here that says X. It gives a parameter, a parameter, parameter, parameter. So for given parameters, this just evaluates to some kind of number. So it's just a number times a Gaussian. But in order to apply this formula, this is the key point, I need to have a Gaussian with the same argument. So going all the way down again, but maybe we can even do it easier here. Now let's just go where we came from. That was probably easier. Yeah, so if I multiply these two, I have a Gaussian in X times a Gaussian in theta, so that doesn't work. But this Gaussian here, the likelihood is actually the Z. I can also write it as a Gaussian over theta with mean X and variance sigma squared. Okay, and then it works, right? Then I can apply this formula. Then I have a Gaussian over theta times a Gaussian over theta. Okay, I can just look at the formula and write down the answer. And basically, if I do that, go back to the formula. Sorry, it's a bit messy. If I do that, so let's say this would be here. This is now a Gaussian over theta. This is a Gaussian over theta. This would be the prior. This would be the likelihood. What I'll get is this will be a Gaussian over theta. This is going to be the posterior. And this term is going to be the evidence. This is just going to be a number. So I can immediately, if I have a Gaussian prior and I have a Gaussian likelihood over theta, I can write down immediately the result, namely the posterior over theta and the evidence, just by using this formula. Is that clear?
Yes, that is clear. So just one other thing. So in the left-hand side, so when we're looking at these two distributions, which are basically, which have the same argument but different parameters, the intuitive understanding is the intuitive understanding that it's the same random variable, but they are distributed like in a different way. Is that how you can understand that?
Yes, absolutely. Absolutely. Yeah.
Got it. Okay.
And the main, I mean, it's a nice property of Gaussians that if you multiply two, if you multiply two Gaussian functions as they are here, and of the same argument, what you get back is an unnormalized Gaussian. You get a Gaussian with some factor. That factor will then turn into, if you interpret it in a machine learning way, and this is a prior, and this here is a likelihood, then this will be a posterior, and this will be the evidence. And so yeah, that's now it's important to realize that, and here is where people get confused, that if you multiply two Gaussian functions, you get a new Gaussian function at the output. The application is to Bayesian inference, where you have to multiply a prior times a likelihood. And what Bayes rule really does is just fuses information from two different sources. The prior tells you something about theta. That's what you know. And the likelihood also tells you something about theta. It's just a function of theta, right? And then if these two sources of information are independent, then Bayes' rule says, well, you have to multiply them. That's just how probability theory works. And we've already, from earlier principles, established that probability theory is the calculus we want to use for this. So that just simple. Now, all the way in the end, this is where people sometimes get confused, is what if we have the product of two variables that both have a Gaussian distribution. Let's say I have a variable x, and x has a Gaussian distribution, and I have a variable y, and y has a Gaussian distribution. And now I want to know what is the probability distribution for z or z. Is that also a Gaussian times a Gaussian? No, that's not a Gaussian times a Gaussian. I mean, it turns out to be an extremely difficult computation, and it involves Bessel functions and stuff. So this is a real problem. You have to really try to think about it and keep that apart. If you multiply two variables that both are Gaussian distributed, then the resulting variable z does not have a Gaussian distribution. But if I multiply two Gaussian functions, yeah, then I get a new Gaussian function. And the real application is not in the multiplication of two variables. The real application is in combining information through Bayes rule, right? I hope that you can think about that, because it's good to keep those two cases apart.
Yeah, thank you.
Okay. Any other question? Okay. This pattern kind of follows how it went last year. Also, in last year's class, you can actually, if you would go to Bayes Lab, Bayes Lab, my lab has a YouTube channel, and so we didn't put them on the website this time here, but there are actually live classes for last year as well, still on YouTube. So you can go to, let's say, last year's class for when we did the Gaussian distribution, and it's just 16 minutes because there actually were also no questions. And it's interesting that we see that pattern repeated. It's also that the case that, so after next class, now the next two classes, right, we are halfway. And around this time, I also did a poll last year. I'm going to do that this year as well. Is checking how people are keeping up or not. And so last year we found out that around this time, yeah, people were kind of losing the pace. And so what we did is in a live class really focused on, okay, let's review everything that we did. So I'm going to do also a poll in Piazza again, asking you to, I mean, you can do this anonymously. It's not about who you are, just want to know kind of numbers or number of people that still feel they're really up to date, or people that are falling behind. And maybe we'll do then, depending on what comes out, we'll do a live class where we just review everything. Also, I found that about half of you voted, and it turns for where this class from 24 December has to go to. And yeah, there's a slight majority for Monday, January 10th, 10:30 through noon. So I'm going to reschedule that class for, basically for this time slot. I hope most of you can follow it. If not, no worries, right? It's going to be recorded and just be online. So that I will do probably today or tomorrow. I will reschedule that class. Yeah, so it's how about last chance, last round for any questions, even if it's outside the Gaussian class. All right, then I think we should, or we can close the session. Please keep asking questions in Piazza, and also I appreciate your efforts in answering questions from other students. I see some really good questions, also good answers. I really like that. Try to keep that active. Don't be afraid to ask questions. And yeah, so then aside from that, I will see you next Wednesday. Next Wednesday, we'll do a it's going to be about a similar class as today. It's going to be now about what if the data is not continuously valued, but it's discretely valued, right? So for throwing dice or coins, that kind of thing. After that, we'll go to real applications, classification, regression, we go to dynamic systems. So then the class will be a bit more towards applications. So yeah, wish you a great weekend and see you Wednesday then. Bye-bye.
Bye-bye. Yep, thank you.